We now talk about universal covering space. So a covering space is a universal covering space if it is simply connected. So consider a covering projection y to x. This covering projection is P, where x is locally path connected and y is simply connected. So you have a universal covering space here. So y is universal cover for x. And say you're given 2 points y1 and y2 and y. So this is space x. There are 2 points y1 and y2 and y. You have the standard covering projection, and both these points get mapped to the same point here. So projection of y1 is same as projection of y2. Now if this is true, then there is a unique covering translation. So you have another copy of y and there is a covering translation. So you have this map theta here. So covering translation means you have this map theta here, and you obviously have this projection map here P again, because this is just a copy of y. So same projection map here, such that this diagram would commute. But the property of this theta is it's going to take this y1 to y2. So you have a unique covering translation, this, which will take theta of y1 to y2. Now the advantage of this lemma is this corollary, which now computes fundamental groups in terms of universal covering space. So if you are given the projection as above, that if you have a universal cover of a space and the projection map just like this, where x is locally path connected, y is simply connected. So if you are given this P as above, and then for any x in this space capital X, the fundamental group is isomorphic to the group of covering translations. So these covering translations form a group. So there could be many covering translations. They form a group, and that group is isomorphic to the fundamental group. So this will be more clear in an example. So the standard example is this. So consider this covering projection from R to S1. So from real numbers to S1. So this is a universal covering space, because you know R is simply connected. So real numbers are simply connected. So you have the conditions here are fulfilled, and you have this map t to exponential of 2 pi I t. So if you take 1 as the base point on the circle, then P inverse of 1 is integers. So let us see this now. Let us draw this. So this is the covering projection. You have the real numbers here, and there is your circle S1, and this is precisely the map t to exponential of 2 pi I t. So this will wrap around the real numbers around the circle. Now P inverse of 1, so you take 1 right here. So this 1 will get lifted here. So it's lifted here. So this might be copy corresponding to, say, integer 0. This might be copy corresponding to integer -1. This might be a copy corresponding to integer 1. This might be a copy corresponding to integer 2. So you have lifting of 1 is all these integers. So it is getting lifted to different integers here. So P inverse of 1 is the entire set of integers. So this is the standard projection map. Now we want to talk about the covering translations. So covering translations are from real numbers to real numbers, and the maps are, you take a real number and you add an integer to it. So this will form a group isomorphic to integers and this addition sign. So let us now draw this. So you could have a covering translation from here to here. So this is again real numbers. So you have a covering translation here to here. So what this covering translation is doing, this will just add a, say, an integer n to each one of these. So 1 will get mapped to, say, 1 plus n, 0 will get mapped to 0 plus n, and this -1 will get mapped to -1 plus n, 2 will get mapped to 2 plus n. Now from here you get another covering translation. So you could add integers here, and this obviously forms a group. So if you go to here theta m, then obviously you add m to it. So this becomes 2 plus n plus m. This becomes 1 plus n plus m. And rather than going like this, you could have gone translated like this, which would be theta. You first add n and then you add m. So you can clearly see this n could be a positive integer or a negative integer, you have a group of this covering translations. So this group consists of elements like this: theta 0, theta 1, theta 2, and so on. And then it also consists of theta minus 1, theta minus 2, and so on. And this is an additive operation. So multiplication of two translation maps is as good as composition is as good as addition. So therefore you have that this these translations form a group which is isomorphic to integers and a plus sign. So you can see you compose n and m and you get n plus m. So you have the fundamental group of circle is same as integers. So this makes our life very easy. So if you want to calculate fundamental group of something, you just find its universal cover and then find the translation maps. Once you have the translation maps, you have the fundamental group. So you don't have to draw loops and then try to find out what your fundamental group is. You can just find a covering space. So let us now prove this lemma. So we have these 2 points y1 and y2 mapping to space x. You have this projection map here from space y. You have another copy of y right here, and you have a projection map here p, and we have to show there exists this unique map theta right here. So first is that we are going to do this in 3 steps. So the first part is we are going to define this map theta, and we are going to show theta as bijective. The second part is we are going to show theta and theta inverse is continuous, and the third part we are going to show is theta is unique. So let us start. So we are going to take a path u starting at y1 in y, project it back onto x, then lift it back to y, that is another copy of y, but it will now start at y2. And then we are going to tie this with covering translation theta by considering the endpoint. So that is quite a mouthful, so let us start. So say you take a path in space y. This starts at y1 and say ends at some point z. Then this path will get projected here. Then you can lift it back up. So if you lift it back up, so since y2 also projects to this x, this path lifts to some point here. So again y1 to z, it goes down to space x. You have projected. When you lift it, it will also start at y2 because both y1 and y2 get projected to the same point x. So p of y1 is equal to p of y2. So you get this path lifted here. So there is some endpoint of the path. So endpoint of the path, you call it theta of z. So endpoint of the path is theta of z. So this is how we are defining theta. So the endpoint of the path is theta of z. So this is how you define this covering translation theta. Now the first thing is we want to make sure that this definition of theta is well defined up to homotopy. So say you take another path. So say you take another path v, which is homotopy equivalent to the initial path which I have drawn in white. So this path will get projected to this path right here. So endpoints are the same. So again this will lift homotopically to here. So up to homotopy everything is the same because you are still preserving the endpoints. So theta of z is well defined. So well defined is fine. Now we have to show theta of y1 is equal to y of 2. Now this can be shown easily if you take y1 equals to z. So if you take y1 equals to z, everything will follow. So let us just draw this. So if y1 is equal to z, instead of a path, what you get is, so this z here, instead of z here, z is exactly at y1. So y1 is equal to z. So you instead have a loop right here. So this loop, this gets carried to a loop right here. This loop will now lift to a loop right here. So that is y2 will be equal to the endpoint of the loop is theta of z. That is how we have defined the endpoint and theta. But theta of z is now equals to theta of y1 because y1 is equal to z. So instead of z, you're plugging in y1. So you have the result. y2 is equal to theta of y1. y2 is equal to theta of y1. Now we want to show that theta is bijective. Now theta is bijective. This can be shown easily by interchanging y1 and y2. So if you interchange y1 and y2, you can do everything in the reverse order, and that will show theta is bijective. So instead of writing y1 here, you write y2 here, and instead of y2, y1. Change everything. That will show theta is bijective. Now we show theta is unique. So say you have any path starting at y1. So say that you have this any path in purple starting at y1. Then corresponding to it, theta will take you to a map. It will take you to point y2, and this theta will map this purple path to the path starting at y2. So this purple is taken here by this map theta. So theta is unique. So it does take the map from starting at y1 to map starting at y2. It does not like take it to any other point just because of this condition. So now we have to show that theta and theta inverse are continuous. So we are going to show theta is continuous, and you can use the same logic for theta inverse. So we are going to show this continuous for this map P inverse of u. So we are going to restrict it to P inverse of u, and in particular say this u is nothing but an open set of x. So say this u is open set of x. So since we are talking about covering spaces, you have to talk about locally, you have to talk about u times d, where this capital D is a discrete set. So we take a copy of it. So say this is u times some copy d1 here, and this is u times some copy d2 here. These are getting projected to P. So there could be multiple copies like this. Now you have a map theta, which is a covering translation between these two copies, and this theta, what is doing is it is taking d1 to d2. So we have to show that theta is continuous on P inverse of u. So this is what we have to show, and this will follow if you take some v which is open in u, and you show that we show this v times d1, this is contained within theta inverse of v times d2. And this is kind of obvious, you know, since v is a open set of u and v is also path connected. So what you do is you take the open set of u, so you take set v right here. So this v will also be here, and this v will also be here, simply because this is u, this is a copy of u, you're just putting an integer next to it, and this is also a copy of u, you're putting an integer next to it. So everything is clear, so you're just taking copies. So if you take a point x here, this point also gets lifted here, and this point also gets lifted here, and theta will map this x to x here. So the difference is this x you will call as x comma d1, this you will call as x comma d2, and this is just x. So say this you will call as point z, and since d1 gets mapped to d2 via theta, this you will call as theta of z. So you can call this point as z, and then you can say there is a path here. So if there is a path here which ends at some point z1, this path will come right here, and this will get lifted to path here, but here now it will end at theta of z1, and that is it. So this is theta of z and theta of z1. So you can see this path is getting mapped to this. So this set here is v times d1, this is getting mapped to here v times d2, and that's what we wanted to show. So now let us come to the proof of this corollary. So we have shown before that this fundamental group, this is iso to P inverse of X. So this was shown in previous lectures, and in this lectures we showed that this P inverse of X is isomorphic to this group G, which is covering translations. So G is the group of covering translations. So you can see this G is the group of covering translations. So let us now just write it more explicitly. So say P inverse of X, say there are 3 points, y0, y1 and y2. So what does group G do? So first focus on just these 2 points. So group G is nothing but, it will give you a map theta taking y0 to y1. Then focus on these 2 points, y1 and y2. So group G would take, say, point y1 to y2. So because you have to find these translations in pairs, 2 points are getting projected to the same base space, then you have a corresponding translation. So y0, y1 you have theta, y1 to y2, say you have phi. So now correspondingly here in the fundamental group you have loops here. You have 2 loops, say u and v, on this base point x. So say you have this loop u and then you have some loop v. So u, this will lift to a path here u, because anyway these 3 points y0, y1 and y2 are all getting projected to this point x, the space point x right here. So this u gets lifted to, say, y0 to y1, and v gets lifted to y1 to y2. So all 3 of them, y0, y1 and y2, all 3 get projected to x. So this composition of loops is same as composition of these maps. So you first apply u and then you apply v. So you go around like this. First u. So first u means you first go theta. The second part is, once you have gone around u, now you go around v. That is same as going around phi here. So that is it. So going around loops is same as composition of maps, and we had given a specific example in terms of the circle. So we had drawn it and shown that composition of maps is same as adding integers, and that is it. So we have covered a very important theorem which basically says that all you need to determine a fundamental group is the universal cover. Once you have this universal covering space of your base space, then you just find its group of translations. So, and those group of translations will give you the fundamental group.